Full history of Pythagoras Theorem from Babylonians to Metric Tensor of Ricci-Curbastro. The story of the Pythagoras Theorem starts with Babylonians and ends with Gregorio Ricci-Curbastro. The full story of the Pythagoras Theorem is not told in one place. Information is scattered in math and historical journals. In this article, I am trying to bring most of the important concepts under one roof, or more aptly, in one article. Pythagoras theorem is a very important theorem. It has been used to define real numbers using Dedekind cuts at irrational number locations in the real number line, which is outside the scope of this lecture. Now let us first look at the Pythagoras theorem that we all know. So in the Pythagoras theorem you have x and y. This is the x and y coordinate system, and it's a flat coordinate system, and you have x distance, y distance, and s squared is equal to x squared plus y squared. There is a problem with this formula. It works only for flat surfaces and orthogonal coordinates that are 90 degrees to each other. Now here we have a sphere, and the angles here at A and B are 90 degrees. So the total angles in this triangle is more than 180 degrees. The above triangle drawn on top of a sphere has two 90-degree angles. The Pythagorean theorem will not work for such surfaces. As I mentioned earlier, the Pythagoras theorem will work only for flat surfaces and up to 3 dimensions. The general theorem that would work for any surface and for any coordinate system and for any dimension was given by Gregorio Ricci-Curbastro and Tullio Levi-Civetta in 1860s, and it looks like below. We will derive this equation in this lecture. ds squared is equal to g mu nu dx mu dx nu. ds squared distance between 2 points. G mu nu is the metric tensor. dx mu is the coordinate system, will be explained later. Dx nu is another coordinate system. So it's a separate coordinate system that we will have to transform. So the derivation of the general Pythagoras theorem that would work for any coordinate system, any dimension, and any surface, curved or flat. So before that, let us see what a tensor is. So what is a scalar? Scalar is temperature, height, the wealth of a person. All these can be represented with one number. What is a vector? Force, velocity. These things need two numbers, one for magnitude and another one for direction. And what is a tensor? Tensor is a bunch of vectors arranged in a very specific manner. Also, they have to transform in a very specific manner from one coordinate system to another coordinate system. The transformation of tensors will be described in this lecture. Now we are going to look at a very famous tensor, and the most famous tensor, that will be the stress tensor. Stress tensor is nothing but an aggregation of vectors, same as Ricci tensor or any other tensor. Wild tensor or Riemann tensor, all those. They all are a combination of vectors. So there are 9 components of a stress tensor, actually more than 9. Some of them are equal to each other, so we could cut it down to 9. So in here you have sigma z c. First z is the direction, and the second z is the area that it's acting upon. Area is this one here, and that area is given by the perpendicular to that particular area, that will be z. And here this is xx. First axis is the direction of the force, and the second x is the area, direction of the area. Direction of the area is the perpendicular to that area. Now here you have the stress tensor, all the forces or stresses, and you really don't need to have two symbols, sigma and tau, but just to separate out, one is a shear stress and the other one is a normal stress. And tensor equation is sigma ij, that would be the stress, and the epsilon is the strain. And here ij means first I is the direction and j is the area that is acting upon. And this force or this stress can affect any strain, can affect any direction. So if you take this stress, this could affect strain in this plane or strain in this direction or any other plane. So since it could affect any direction, so we have to come up with another letter, and that we call it K, and it could affect any area, so we have to come up with a fourth letter, and that let's call that L. So now we have 4 letters, and then the parameter that combine these two forces or stresses should have 4 indexes. So the direction of an area is defined perpendicular to the area given. So this is basically, if you want to get the direction of ABCD area, you just draw perpendicular and that would be your area. The direction of the area ABCD is given by the arrow sigma xx. Here first x means the direction of the force, second x means the direction of the area or the line perpendicular to that area. Now let us look at how tensors transform one coordinate system to another. First we need to define the coordinate system. So let us call x, y, z coordinates to be x1, x2 and x3. So there's nothing wrong in doing that. So x we call it x1, y we call it x2 and z we call it x3. And we can go for more dimensions, 4, 5, 6, etc. if you want, if you have more dimensions. The second coordinate system to be used would be y1, y2 and y3. A vector in the x coordinate system can be represented as below. A equals sigma ax. Now let's say we have n dimensions. So the vector A would be a1 plus a2 plus a3 all the way up to an. And if it has only 3 dimensions, then it will be a1 plus a2 plus a3. So in this representation, we could represent all the way up to n dimension. Here A is the vector. It has components a1, a2, a3, a4 all the way up to an. For simplicity, let us remove the sigma symbol. We really don't need it because it's obvious. And just call it axn. So here x is the x coordinate system, n is the number of dimensions. If it's 3 dimensions, n would be 3. So in that case, ax1 plus ax2 plus ax3. Which means the representation of vector A in the x coordinate system, x1 through xn. Now as we discussed before, a tensor is nothing but a combination of vectors, but they need to have certain properties such as differentiability, etc. Let us consider 2-vector tensor. As I said, the tensor is a combination of vectors. So very simple one is 2 vectors. Now these 2 vectors axn and bxn could be dot product, could be cross product, outer product, inner product, whatever. And that would create a tensor. Now if it's the dot product, this tensor would be a scalar. And if it's a cross product, then that would be a vector. Now we need to transform this. Okay, before we go to the next step, axm means x coordinate system up to m dimensions. Bxn means x coordinate system up to n dimensions. Now we need to transform the tensor txmn to y coordinate system. First let us transform the 2 vectors. There are 2 types of vectors. They are contravariant vectors and the covariant vectors. Let us consider contravariant vectors for example, because most vectors are contravariant. Covariant vectors are needed to transform basis vectors or gradient vectors. The basis vectors are basically unit vectors, and if you are going to transform them, then you have to consider them as covariant vectors or the gradient vectors. Typically, covariant vectors come into play when the distance is in the denominator, as in the case of the gradient or basis vectors. So this is the transformation. AY means a vector in the y-coordinate system. R means the dimensions, whatever the dimensions in there. And this is the partial y or partial x is the change in y with respect to x. So we have m dimensions in the x-coordinate system, r dimensions in the y-coordinate system, axm. Let us take a small example. Now I created this example. Let us assume I have 10 jobs producing 10 wages and 8 savings account. Let us assume my savings are proportional to my wages. Let's say my wage is W and my savings is S. Hence we can say change in savings is equal to rate of change of savings in relation to wages times change in wages. So if my wages goes up by a certain amount, then we know the rate of change of savings in relation to wages, and then you multiply the two, and then I could get the change in savings. Rate of change of savings in relation to wages is partial S or partial W. Change of wages is dW. Change of savings is ds. Hence we can say ds equal partial S or partial W times dW. Similarly, we can transform the other vector bxn into bys. Partial ys in y-coordinate system, and we have s dimensions. X-coordinate system, we have n dimensions, bxn. Actually, n should be up there here because we are dealing with contravariant vectors. I made a mistake here. Now you may wonder why in our wages and savings example do not have subscripts such as S, N, M, etc. We assumed I have 10 jobs and 8 bank accounts. Let us assume they are all interconnected. Now why we don't have these subscripts in the wages when we have here in this here, because we really don't have dimensions as such. So my total wages, as in addition of all the wages, is, let us call all the wages from 10 jobs W1 through W10. Now my 8 savings can be represented with S1 to S8. Now they don't have to be equal, they don't. Let us assume I got a raise in job 1, so W1 goes up by DW1. This additional money I allocate to all the savings accounts by a known pre-decided rate, DS1 plus DS2 all the way up to DS8. I have 8 savings accounts. This can be represented in a short form. DS1 is equal to partial S or partial W with relate to 1 times dW1. So similarly, DS2 is equal to, that means here how much savings went up in my savings account 1 due to the raise in the job 1. Here how much savings went up in my savings account 2 due to the raise in job 1. Again DS3, how much raise or how much savings I went up due to the job 1, etc. So we can generalize this DSM 1 through 8, partial S or partial W, and 1 through 8, and W is always 1. As you could see, always 1, so 1 stayed the same. DW is always 1, so 1 stays the same. M changes from 1 to 8. Now we have 10 jobs to account for, hence we need a summation sign for W as well. So we could do this for DW2, DW3, DW4, etc. So we need a summation sign for the DW also. So DWR, and M equals 1 to 8 and W equals 1 to 10. So in this case, we don't have to represent axes. We don't have axes here. We just have only numbers, scalars. So now let us go back to tensors. We can combine the two transformations, equations 1 and 2. I have equation 1 is here, transformation of a vector in the x coordinate system with m dimensions into transformation of a vector in the a coordinate system in the y coordinate system with r dimensions. It's the same vector. The vector doesn't change, only the components will change, and partial y over partial x is the rate. So those two can be combined here, two vectors bxn and axm, and these are the partial, the rate of change, and we could take axm here outside and then keep this partial here. So AYRBYS is a tensor in the y coordinate system. Let us call it TYRS. BXN is a tensor in the x coordinate system. Let us call it TXNM. So AX and BX, we call it TXNM, and we call this one here TYRS. So hence we get this equation. In this case, the tensor is only two vectors. One can have any number of vectors, also mix up covariant vectors and contravariant vectors. So now let us take 2 points. Point 1 has coordinates x1, x2, x3, and xn. And a small change in x can be represented by dx equal dx1 plus dx2 plus dx3. Now this is a vector addition. As explained earlier, when we transform small dx vectors to dy coordinates, we will get the following. So dy1 is the partial y or partial x, change of y due to change of x, and dx1. And then similarly we have dx2 and dx3, all that has to be added in. So similarly dy2, we also can have the same equation written down, and then we would get a general equation. We did this before, and you could go back and see how we got this. So 1 through m could be dym, and 1 through m here dy the partial ym. 1 x goes through n, 1 through n, and dxn here. So now let us consider 2 points in the x coordinate system. So x dx1 and dx2. So we can say ds squared is equal to dx1 squared plus dx2 squared. If you have n dimensions, we can write ds squared is equal to dx1, 2 to all the way to n. Or we can write ds squared is equal to sigma dxm and dxn. And then for flat surfaces with m and n dimensions, you would call something called delta, which is a Kronecker delta, when the property is when m equals n, delta equals 1, otherwise delta equals 0. So if we have m equals 1 and n equals 1, so it would be dx1, m equals 1 and n equals 1, so dx1 squared, and in that case delta is 1, that dx1 squared stays. If m equals 1 and n equals 2, they are not equal, then delta is 0, that term becomes 0. So for flat surfaces, you get the Pythagoras theorem here. Now there is some explanation needed here why there could be m and n dimensions. Here we are doing mathematics and not physics. In real world or universe, every coordinate system will have only 3 dimensions. With the time dimension added will be total of 4. But mathematical equations can be developed to transform from n dimensions. In mathematics, you could take any dimensions. Whether they exist in another universe, somewhere, reality, it doesn't matter. Now, as I showed earlier, how we can transform to different coordinate systems. Let us call the new coordinate system y coordinate system. So dxm is the partial of x changed to y and dyr. So similarly, we get dxn is the partial of x changed with relative to y and dys. Hence, following equation can be written in y coordinates axis. So ds squared is equal to sigma dxn dxm. We can replace these for dxm and dxn, and we did this before, so I'm going fast here. Now I'm going to remove Kronecker delta because we really don't need it anymore. We're not looking at flat surfaces. We're looking at any surfaces. So the Kronecker delta goes out the window, and you get this equation. This is a partial, and this is the vector, and this is the other vector. So these two vectors can be taken out, and normally sigma sign is removed since it is pretty obvious. So this term is given the name the metric tensor, G nu mu. So this equation can be written as this way, and we could apply G mu nu to here, and we could just change dy to dx. There's nothing wrong in doing that. There's no reason why you can't call it dy. I just use dy. You could just use dx. So this is our general equation, and this would work for any surface, for any dimension, mu or nu. These are the dimensions, and this is transformation from mu to new dimensions, and this is the metric tensor, and this is the distance. So the above is the general formula of Pythagoras theorem for any dimension and for any surface, any type of curve. Only requirement is the coordinate system. The technical term for the coordinate system is manifold. Well, it's not really true. That's not true. The manifold has to be smooth and differentiable. For example, a sphere is a smooth manifold, and sphere is not a coordinate system. Sphere lives inside a coordinate system. So I'm kind of wrong here. So while a cone is not a smooth manifold, cone is not a smooth manifold because there's a vertex, and that's not smooth there. You cannot differentiate at the corner, at the edge. So this is the general theorem. Now we go back to the Pythagoras theorem, Babylonian. So the Babylonians were the first to use Pythagorean triplets to create right angles. Pythagorean triplets are 3, 4, 5, 5, 12, 13, 8, 15, 17, etc. If you create a triangle with sides 3, 4, 5, one of the angles would be a 90-degree angle. 90-degree angles were needed to build buildings, surveying, etc. Did Babylonians state the Pythagoras theorem? The answer is no. Let us look at a Babylonian tablet. Here you have numbers. These little signs are numbers converted to modern numbers here. In this tablet, side of the square is given to be 30. So the square here, one side is 30. Then the diagonal should be, so this diagonal should be 30 squared plus 30 squared, 42.42. I just calculated that. Now Babylonians worked in 60 base. You can see numbers 42, 25 and 35. 42, 25, 35. See these numbers here, 42, 25, 35. That's there. In 60 base, 42, 25 is 25 over 60, 35 is 35 over 60 squared, etc. And it comes to 42, 42, 63. Exactly. Now the question is, how did they get it? Did this equation, or they just measured it? So they were able to figure out the diagonal of a square. But how did they do it? Did they use geometric methods or arithmetic methods? We don't know. They could very well draw a square to scale and measure it. You could draw a square with this scale and then you measure the diagonal. Did they knew this formula? We cannot tell. They didn't state it. So now what are the numbers 1, 24, 51 and 10? They add up to 1, 24 by 60, 51 over 60 squared, 10 over 60 cubed actually. So it adds up to 1.4142. This is the square root of 2. So they did some calculation here. So if 1 and 1, then square root of 2 would be the diagonal. Diagonal of square with sides 1 would be 1.4142. Now multiply this number by 30 and then you get 424263. So they did not really have the Pythagoras theorem as such. They didn't have this theorem, but they did a shortcut. They did 1, 1 and then multiply by 30. That's what they did. So they didn't state. But unfortunately this works only for squares. As you could see, they use special method that will work only for two bases are equal. This method will not work when you have, let's say, 3 and 4. So it would work 3 and 3 or 5 and 5, etc. But there were other clay tablets with rectangles with unequal sides, and then these kinds of numbers were formed. These numbers were written down in Babylonian clay tablets. Some of these numbers were so-called Pythagoras triplets, such as 3, 4, 5. It does mean that the Babylonians had the Pythagoras equation. I'm not convinced. They knew about it. They did various other ways. They were using geometric methods or special methods such as finding square root and multiply with a number, etc. Or there's no reason to create a tablet of Pythagoras triplets if they knew the theorem. But why would they need tables if they had the theorem? But one can argue computation was time-consuming and it would be easier to use tablets. All these arguments can be made, but the bottom line is they did not state the theorem. So who stated the theorem for the first time? And that would go, Pythagoras theorem was stated for the first time in Bauddhyana Silva Sutra. First general statement of the Pythagoras theorem was given in Bauddhyana Silva Sutra, and they did not give a proof. Pythagoras theorem was first stated by this one here, Dirgha, Chatushraya, Akasnaya, Raju, whatever here. A rope stretched along the length of the diagonal produces an area, but it doesn't really say area here. This translation is not really correct. I don't see area, which the vertical and horizontal sides make together. But it means that you're not going to add the two sides. It has to be the square. So this is a general statement. This is well accepted among European scholars, and Bauddhyana Silva Sutra is dated to 700 BC. Indians never proved the Pythagoras equation. In fact, they never proved anything. Proving was not part of Indian mathematical tradition. Then who proved the Pythagoras theorem? Pythagoras theorem in Greece. Euclid. Very first proof for Pythagoras theorem comes to us in Euclid's Elements. All agree that Euclid was not an inventor like Archimedes, Apollonius, Thales, etc., but a scholar who wrote down the knowledge that existed at that time. Later Greek and Roman historian Proclus wrote that Euclid got the proof from Pythagoras. How credible is this when Pythagoras lived 500 BC? Any concrete evidence? No. But we can say that proof of Pythagoras theorem was around for a long time before Euclid. We can make that assessment since Pythagoras theorem was a much easier theorem in Euclid's geometry books. There were very difficult theorems proved in Euclid's many books. Pythagoras theorem in China. Chinese proof in 9 chapters of mathematics. Chinese ancient mathematical book had a diagram that seems to indicate the proof of the Pythagoras theorem. Bhaskara, an Indian mathematician, had the following interesting diagram. He just said, behold, prior to Bhaskara, this figure appeared in 9 chapters of mathematics. So this figure here, full square is, this is C, this side is C. The full square is C squared. Sides of one triangle is A, this side is A, and this side, this is B, and this is A again. So area of one triangle is half A times A plus B. This is the area of one triangle. Area of 4 triangles, there are 4 triangles here, would be 2A squared plus AB. Simplify this. Total area inside the square is C squared. It should be C squared. B squared plus 2A squared plus 2AB. B squared is this square plus the 4 triangles. So imagine a triangle with sides A and A plus B and the diagonal of C. Then C squared is equal to A squared plus A plus B squared, and it would simplify to here, it simplify there, and that equals this, and that's your proof. So it's a very simple, very elegant proof. So this is what I found in the internet for what happened. This is the Bhaskara's proof, but he got it from the 9 chapters of the Chinese book. This also can be used to prove, this is another diagram here. Let us assume the side of the largest square is the same thing. You could go through this, it's the same thing. Now the big question is the Chinese proof older than Euclid's proof? Now I did not give Euclid's proof, it's available everywhere in the internet. So it's a pretty long proof. But the question is, who proved it first? We don't know. We don't know if the Chinese proof is older than the... So the summary. Babylonians started to use the so-called Pythagoras Theorem triplets around 2000 BC, but they never stated the theorem. Bauddha and Sulba Sutra first stated the general Pythagoras Theorem around 800 BC, 700 BC, whatever. But he never proved it. Euclid proved the Pythagoras Theorem. So as the Chinese. But which one is older? We don't know. So, and Pythagoras Theorem applies only for flat surfaces with 2 or 3 dimensions. And for curved surfaces for any dimension, for any coordinate system. That was done by Ricci-Curbastro. Thank you very much for listening.